How many branches of physics are there? Physics before the 20th century had primarily three branches: classical mechanics. Classical mechanics is concerned with the motion of objects under the influence of forces. There are three main formulations of classical mechanics: Newtonian mechanics, which involves Newton's laws of motion. These laws described an array of different dynamics, including rolling balls, swinging pendulums, and planets in orbits. Lagrangian mechanics arose from the Newtonian formulation as a result of how difficult it was to solve systems that were complicated or involving many objects. Lagrangian mechanics was developed independent of any particular coordinate system. The formulation involves defining the Lagrangian and the development of calculus of variation. This led to solving many complicated problems and, more importantly, the discovery of the principle of least action. Hamiltonian mechanics formulation is based on a Legendre transform of the Lagrangian of a system. Hamiltonian mechanics is focused around emphasizing the conserved quantities and symmetries of a system. Technically, all three formulations are mathematically equivalent and essentially describe the same set of rules. Which one you use depends on the problem and what you are trying to extract from a system. Statistical mechanics, the very powerful idea that matter is made out of classical atoms that bump around and exchange heat, forms a basis for statistical mechanics. Simply put, we can describe macro properties like pressure and temperature due to the random interactions between atoms. Electromagnetism. In the 19th century, electricity, magnetism, and light were studied separately. Thanks to several scientists, most notably Ampere and Faraday, a few laws were formulated. Later Maxwell came along and unified electricity and magnetism, and showed that light was an electromagnetic wave as well. Early 20th century physics, relativity, special and general, quantum mechanics. Research in physics nowadays uses those branches to solve problems in high-energy particle physics, gravitational physics, and cosmology. Astrophysics and astroparticle physics, atomic, molecular, and optical physics, AMO, nuclear physics, condensed matter physics, computational physics, to name a few things on the top of my head. Finally, this list barely scratches the surface of fundamental physics, theoretical and experimental. There's a whole sea of other branches in applied or interdisciplinary physics, biophysics, geophysics, etc.